Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 16, 2026, about 4 days ago. It uncovers a critical mechanism where models trained with reinforcement learning can bypass genuine reasoning, instead activating a specific internal circuit to retrieve memorized answers. The paper is titled Spurious Rewards Paradox, Mechanistically Understanding How RLVR Activates Memorization Shortcuts in LLMs. And as we'll see, the ability to pinpoint and even steer these specific neural pathways offers a promising new way to detect data contamination. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 presents the empirical evidence for this paradox. The bar chart on the left compares the base model in blue against versions trained with correct, random, and incorrect rewards. Crucially, look at the yellow bars for Math 500 and the NervaMath. These represent training with incorrect rewards, yet performance skyrockets compared to the base model. This implies the model is retrieving answers rather than reasoning. In contrast, Live Math Bench on the far right shows almost no gain, serving as a clean control. Finally, the pie charts on the right help isolate the specific questions that flip from wrong to right, identifying likely data leakage. Well, Figure 2 confirms this hypothesis using partial prompt evaluation, where the model must complete a question given only a fraction of the text. The top row measures text similarity using Rouge L scores, while the bottom tracks exact completion accuracy. Focus on the Math 500 panels on the left. The solid green lines, representing questions the model learned to answer, rise sharply compared to the dashed baselines, meaning it recognizes the test data. Conversely, the Live Math Bench panels on the right remain flat. This gap proves the model isn't learning to reason better. It is simply recalling memorized examples from the contaminated dataset. So, Figure 4 visualizes the statistical footprint of this behavior, which the authors term the perplexity paradox. Focus first on the orange charts on the right, which track the perplexity, or uncertainty, solely for the answer tokens. This metric drops sharply during training, meaning the model becomes highly confident in these specific outputs. However, the blue charts on the left show that perplexity for the full text actually rises. This divergence confirms that the model is trading general linguistic coherence for narrow, memorized accuracy. Alright, moving to Figure 7, we see the mechanistic explanation for this behavior using LogitLens. The top row tracks a successful run where the model retrieves the correct answer, 4. In the second chart here, a precursor signal appears at layer 19, and by layer 23, indicated by these green bars, the model aggressively locks on to the memorized solution. Now compare this to the bottom row, which shows a failure case, even though the model outputs the wrong answer. 3. Look at the heat map on the far right. The dark red blocks at layers 23 through 25 reveal that the model still tried to inject the correct answer, 4. This proves the memory exists, but the initial trigger in the middle layers was simply too weak to override the error. Okay. Figure 10 validates this mechanism using neural differential equations, a framework that models the network's layers as a continuous flow. The chart on the left tracks separation force, which measures the directional pulls separating reasoning from memorization. Notice the sharp peaks marked with stars at layers 18 through 20. This confirms that these anchor layers are responsible for the initial steering. Conversely, the right chart shows the velocity difference, or the strength of the signal update. Here, the activity spikes later, at layers 23 through 25. Proving that these subsequent layers amplify the shortcut decision. So, Figure 13 demonstrates the power of this discovery through causal steering, where the authors manually scale neuron activations. On the left, for the leakage datasets, the heat map tracks accuracy changes. Notice the distinct row for layer 18. Scaling it up boosts accuracy by over 4% in deep red, while scaling it down causes a sharp drop in blue. This essentially confirms layer 18 acts as a control switch for memorization. By comparison, the right panel shows the leakage-free benchmark. Here the results are random and faint, proving that this intervention specifically targets the contaminated pathway without harming general reasoning. Wrapping up, 2 takeaways stand out. Spurious reinforcement learning signals act as a mode switch, activating a hidden anchor adapter circuit to retrieve memorized data instead of improving reasoning. Consequently, this provides a mechanistic roadmap for detecting data contamination in future models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.